Okay, welcome back again. We continue with one example. We have a homogeneous sphere of mass m and radius r, which is projected along the incline of angle theta with an initial velocity v naught and no angular velocity. If the coefficient of kinetic friction is mu k, determine the time duration t of the period of slipping. In addition, state the velocity v of the mass center g and the angular velocity omega at the end of the period of slipping. So we assume we have a coordinate system x, y, which x is an axis parallel to the inclined surface and y is perpendicular to the inclined surface. So we have one sphere with mass m and radius r with velocity, initial velocity v naught, which is released on this surface with friction, coefficient of friction mu k. Initially, this sphere start to slip, and after the slipping, it start to rotate. Okay, so we want to obtain the period of time t, which is the period of slipping. So we can write for this example again the impulse momentum equation. If you write the impulse momentum equation in y direction, since there is no motion and there is no velocity in this direction, so the impulse is equal to 0 in this direction. And if you write the force equation in y direction, we will have one normal reaction here. We have the friction force, which is parallel to the surface, and also we have the weight. So this weight will have two components in x and y direction. So the y component of the weight, which is mg cosine theta, it's equal to n from the impulse momentum equation in y direction. We can write the impulse and momentum equation in x direction. So we will have the summation of the force in x direction, the impulse of the summation of the force in x direction. It's equal to the variations in the linear momentum, which is mvx minus mvx x naught, which vx naught is the v naught, this initial velocity, this term. Okay, so we will have the summation of the force in x direction, which is mg sine theta, the x component of the force in x direction. And also we have the friction force, which is mu k times by n, and n is mg cosine theta. From the first equation here, we obtained that n is equal to the vertical component or y component of the weight. So we can substitute here, it must be equal to mv minus v naught, which v is the velocity of the mass center after t seconds, and v naught is the initial velocity, which is the given data in the problem description. So from this equation, we can obtain that t is equal to v minus v naught g sine theta minus mu k cosine theta. In this equation, all of the values are given except this one v, and v is another unknown in this equation. So v and t, both of them are unknown, and now we need another equation to obtain v and t, because there is one equation with two unknowns. So we need another equation to solve and find these two unknowns. So we know that we can write the impulse momentum and angular momentum equation. About the mass center, we can write this equation. When you write the impulse angular momentum about the mass center, g, it's equal to mu k times by nr, because the weight is located on the mass center the normal force passing through the mass center. So these two forces, they don't have any moment. There is no moment due to these two forces, and only the friction force, which is mu k times by n, will have the moment about the mass center multiplied by its arm, which the arm is the radius of the sphere. So summation of the mg is mu k n r, and in the right hand side we will have the mass moment of inertia about the mass center times by omega minus omega naught, which omega naught according to the problem description is equal to 0. Here if we come back to the previous slide, here, and initial speed v naught and no angular velocity. So the initial angular velocity is 0, and we can substitute here instead of omega naught, we can substitute 0. I bar for a sphere, we know the mass moment of inertia about the mass center is equal to 2 divided by 5 times by mass times by the radius squared. So we can substitute again, instead of n, we will have mg cosine theta times by r times by mu k and times by t. It's equal to 2 divided by 5 m r squared times by omega. So we can substitute here. We will have another equation or another relation between t and omega. Okay. And also we can assume that because after the sleeping, the motion is rotation without sleeping. So we can assume that V in this equation here, this V is equal to R omega. So we will have two equations with two unknowns, and we can solve these two equations to find T and omega. So from these two equations, we can conclude that T is equal to T. So this term from the first um, equation is equal to this term from the angular momentum equation. So here in these two equations, if we solve and simplify this equation, we can extract omega from these relations. We will have mu k cosine theta r v naught, and only we have one unknown omega. In the right hand side again we have one unknown omega. We can simplify and extract that omega is equal to this term, and we can obtain the final angular velocity for that sphere. Okay, and here we have another example. The 30 kilogram wheel has a radius of gyration about its center of 75 millimeter and is rotating clockwise at the rate of 300 revolution per minute, or RPM. When it is released onto the incline with no velocity of its center O, while the wheel is sleeping, it is observed that the center O remains in a fixed position. Determine coefficient of kinetic friction, mu k, and the time t during which sleeping occurs. Also determine the velocity v of the center 4 seconds after the wheel has stopped sleeping. So again, if you plot the free body diagram, we will have the weight, the friction force, and normal force. We assume axis x, which is parallel to the surface, inclined surface. So during the sleeping, since there is no motion and the wheel is rotating and its point, the mass center point O will stay here and there is no acceleration. So we can write the force equation in x direction. So during this time, the summation of the force in x direction is equal to 0, and we can conclude that the F, which is the friction force, and it's equal to mu k times by n, it's equal to mg sine theta, the x component of the weight. So from here, we can conclude that mu k is equal to tangent theta. The next step, we need to calculate the time of the duration for the sleeping. So we can write the moment and angular momentum about point O. The moment about point O is equal to the force F times by its the radius, which is this length. So F times by R times by T, this is the integrated form of the impulse angular momentum equation. So FRT, which F is again equal to mu times by N, FRT is equal to delta HO, or the variations in the angular momentum. The initial angular momentum is equal to 0, and the final angular momentum is equal to 0, and the initial angular momentum is equal to IO times by omega, which omega is 300 RPM, which we converted into radian per second. So we can find from this equation, we can find time t by I o omega dividing by f times by r. And as I told you, f is equal to mu k times by mg cosine theta. So we can substitute the numerical value and calculate the time t. Now we need to obtain the velocity, angular velocity after 4 seconds. Here, this is. So we can write the force equation, impulse and momentum equation. But after starting the motion of the wheel on this incline, we will have two options. One is with sleeping and the other one is without sleeping. So we can assume that the motion is without sleeping. So when there is no sleeping, so the velocity of the mass center is equal to the angular velocity times by the radius r omega, and we can find the omega from impulse momentum equation. So the impulse equation in x direction, we can write it. In x direction, we will have the x component of the weight mg sine theta minus the friction force, which is F times by T. It must be equal to the mass times by the variation of the velocity. And we know that this will start from rest, because at the initial position, it doesn't have any linear velocity. And V is the final velocity after 4 seconds. And it's equal to r omega according to the assumption of no sleeping. So we can substitute here and calculate. And also we need another equation, because this equation includes two unknowns. One is the F, the friction force, and the other one is the velocity of the mass center. This friction force is not equal to the mu k times by n, because we assume that there is no slipping, so it's not the kinetic friction force. Okay, so this is a friction force which should be calculated and compared with the maximum value of the friction force. So we need another equation. The second equation can be obtained using the angular momentum impulse equation. So the moment about point O again is equal to RFT, and T is the time from 0 to 4, and it's equal to 4 in this case. IO is the mass moment of inertia about point O, or about the mass center that we have the radius of gyration. Easily we can calculate IO. And again, the initial velocity is 0. And the final velocity, angular velocity, is the linear velocity divided by r. We know that v is equal to r omega, or we can substitute instead of omega, v divided by r. So we have two equations with two unknowns, and we can solve them. From these two equations, we can obtain V is equal to 4.3 meter per second and F is equal to 18.3. If we compare this F with the friction force, the maximum friction force, because in this problem, we don't have the coefficient of static friction force. So we can calculate the kinetic friction force, which is mu k mg cosine theta, and it's equal to 51.1. You can see the kinetic friction force is more than this friction force, calculated one, 18.3. And also we know that the kinetic friction force is always less than the static one. So the maximum friction force is definitely more than 51 and F is less than 51. So definitely F is less than the maximum friction force, which is the static one. So our assumption is correct, and we can consider this velocity as the final velocity after 4 seconds. Okay, so this is the total procedure to solve this problem using the uh, impulse and momentum equation. Also, we can solve this example using the Newton's second law. Here I solve this example using the Newton's second law. By using the Newton's second law, we will have again the force equation in x direction. Again, we assume that we have motion without a slipping. So in x direction, we will have mg sine theta minus f. It's equal to the mass times by ax, which is the acceleration in x direction. And due to the our initial assumption, ax, or the acceleration of the mass center, is equal to r alpha, which alpha is the angular acceleration of the wheel. And then we can write the moment equation about the mass center. If you write the moment equation, we will have the moment due to this force F, and there is no moment due to the force N and the weight. So it's equal to R times by F. It's equal to IO times by alpha. So we have two equations, 1 and 2, this one and this one, with two unknowns, F and alpha. We can solve them and obtain alpha and F, which again, you can compare this F with the maximum value similar to the previous method. And you can conclude that this F is less than the maximum value. So your initial assumption is correct. It's validated, and we can obtain that omega is equal to alpha t, because the acceleration is a constant value. So after 4 seconds, because omega start from 0, so it's equal to alpha t plus 0, which is the initial angular velocity, and t is 4. So easily you can calculate that omega, or the final angular velocity, is 43.56. Okay. And this is exactly the same as here if you calculate the omega from V, because omega is V divided by R, and R in this case is 0.1. It will, the omega will be 43.5, and it's exactly the same which is calculated here in the second method. Okay, and this is the suggested problems for this chapter. By this example, in fact, we wrap up this chapter and the concepts for this semester. For the next week, we will review the previous chapters, and we will have a revision week. Okay, thank you for your attention, and bye.